Good morning, everybody. Let us go to the next session on instrument transformers. Again, the purpose of instrument transformer is to again measure current and voltage, but of higher range. So there is a limitation over the current that can be measured using ammeters and voltmeters and even the multipliers and shunts. So if you want to measure current and voltage of higher range, we have to go for instrument transformers. Instrument transformers are of two types: current transformer and potential transformer. Current transformer for the measure of current, and potential transformer for the measurement of voltage. So let us first discuss the drawbacks of shunts and multipliers. Then we can go for instrument transformers. Shunts and multipliers are suitable only for measurement of current and voltages up to 100 amperes and 1000 volts. So beyond this range, we have to go to ITs, instrument transformers. Then there is a difficulty to achieve accuracy in current division between the meter and the shunt when it is connected to AC supply. This is the second disadvantage. Third one, it is difficult to design insulation between the shunt and the coil at high voltages. Whenever we are operating at high voltages, we should take care of the insulation between them, because there is always a probability of failure of the insulation, and it may result in short circuit. Fourth one, there is no electrical isolation between power and measuring circuits in shunt. This is very much essential. So if there is no isolation, again it will result in problem. Fifth one, at high operating voltages, the instrument power consumption increases, which is not desirable for an instrument. In the beginning itself, we discussed about the essential characteristics of a measuring instrument, which is the instrument itself must not consume more power. It should always consume least as the power as least as possible. But when we try to operate at higher voltages, there is a probability that it can consume more power. Last one, insulation provided to prevent the flow of leakage current in multiplier is expensive. Whenever we go for higher voltages, the insulation design also becomes expensive. So these are the drawbacks of shunts and multipliers. So with this, we'll go to instrument transformers. First one, current transformer. Essentially, the current transformer is a step-up transformer. Voltage gets stepped up, current gets stepped down. So as per the definition, CT is a type of instrument transformer that is designed to provide secondary current proportional to the current flowing in primary. So this is the schematic where we have the load. The primary of the CT, primary winding of the CT is connected in series with the test circuit whose current is to be measured. So our intention is to measure this IP flowing in the primary. So we connect an ammeter in parallel to the secondary winding of CT, and the current flowing is IS, and secondary of CT is grounded, and the range in this particular case we have given 0 to 5 amperes. Generally in a CT, primary will be having fewer number of turns, secondary will be having more number of turns or large number of turns. So coming to the CT, again, since this is also a transformer, it works on mutual induction principle. Voltage gets stepped up, and then current gets stepped down by a definite ratio as per the design. So the governing transformation ratio expressions are V2 by V1 is equal to N2 by N1 is equal to I1 by I2 is equal to K. We know that I2 is equal to I1 divided by K. So the purpose of CT is to reduce the primary current to the readable range of the meter. So the readable range of the meter is 5 amperes. So that will get reduced to 5 amperes. So once the deflection is shown in this ammeter, that when multiplied by the transformation or CT ratio, we will be getting the actual IP reading. So let us see how it goes. Generally, we define CT by its ratio called as CT ratio. Say we say 100:5 CT, for example, reduces the current from primary to secondary by ratio 100/5, which is around 20 times. So it is defined as ratio of primary current to secondary current. The actual definition of CT ratio is primary current to secondary current. Applications: metering, protective relays, and for safe measurement of large currents in high voltage appliances. Next, we'll go to potential transformers. So PT is again an instrument transformer that reduces high alternating voltage to a value which is measurable by the meter. So here we can see on the high voltage side, our intention is to measure the voltage. So here the primary will have large number of turns and secondary will be having fewer number of turns, and a voltmeter is connected across secondary. So here the secondary has got a range of 0 to 110 volts. Here this is essentially a step down transformer. Voltage gets stepped down. So the operating principle, again mutual induction, V2 by V1 is equal to K. So V2 is equal to K times V1. Again we define PT ratio. It is defined as the ratio of rated primary voltage to the rated secondary voltage, V1 by V2. Next we'll talk about errors in CT. One of the errors is ratio error, the other one is phase angle error. So let us see what is this ratio error. Whenever the transformation ratio is not equal to turns ratio, it results in ratio error. Actually, turns ratio should be equal to transformation ratio. That is V2 by V1 should be equal to I1 by I2 should be equal to N2 by N1. But in case of the ratio error, the turns ratio will not be equal to the transformation ratio. That is called as, the deviation is called as ratio error. The primary current basically is composed of both core component and magnetizing component of current. So because of this magnetizing component of current, most of the time the turns ratio will vary from the transformation ratio. Secondary current basically will be dependent on nature of the load. So if you go for the definition or expression of the ratio error, not the definition, expression for ratio error, it is given by nominal ratio minus actual ratio divided by actual ratio into 100. It is given by Kn minus R by R multiplied by 100. Kn is IP rated by IS rated, primary current rated by secondary current rated. Actual ratio is equal to IP actual by IS actual, and R is given defined by N plus Im sin delta plus Ic cos delta divided by Is, where Im is magnetizing component of current, Ic is core component of current, and then delta is the phase angle difference between secondary voltage and secondary current, and Is is secondary current, N is the turns ratio. Under ideal conditions, Kn must be equal to R such that the error is 0. But practically there exists a difference between Kn and R. Next one is phase angle error. So the currents and voltages in primary and secondary of a transformer undergo a phase shift of 180 degrees, as we very well know. But practically phase shift will not be exactly 180 but differs by a small angle called theta, that is nothing but defined by phase angle error. Expression is 180 by pi into Im cos delta minus Ic sin delta by N into Is. So these errors can also be approximated by some assumptions. That is nothing but delta usually, since the load happens to be predominantly inductive, delta is very small and can tend to 0. It is almost close to 0. If you consider 0, sin delta will be 0, cos delta will be 1. Then R will be equal to N plus Ic by Is. So if you go to the expression for R, here we have Im sin delta, that term will become 0. Ic cos delta will be only Ic. So it will be N plus Ic by Is. Or it can be written as N plus NIC by IP if you express in terms of primary current. So the percentage ratio error will be Kn minus R by R into 100. Similarly, even if we take phase angle error, it will be 180 by pi into Im cos delta minus Ic sin delta by NIS. Go for the assumption sin delta is 0, so the second term will vanish. First term will just contain Im. So approximate error will be 180 by pi Im by N into Is, or in terms of primary current 180 by pi Im by Ip. So these are ratio errors and phase angle errors. In the next session, we'll talk about error minimization in instrument transformers.